All right, let's talk about these three special kinds of frequency distributions, which are called relative, cumulative, and grouped. I think that the relative uh, frequency distribution is probably going to be the most enduringly important one in this class. The cumulative frequency distribution we won't see very much. It does come up in the week 2 discussion if you end up doing the online discussion. And grouped frequency, we'll see a little bit of that too. It does occur on homeworks. Okay, so I want to go back to the example with the children and the families. This was the basic table that we got here. So there were zeros, ones, twos, threes, fours, and fives in the list, which again represent numbers of children. Thank you. Which occur in this number of families, 3, 5, 7, 6, 3, and 1. So those two columns are repeated right here. What I'm doing now is I'm taking these whole number frequencies and I'm converting them into fractions, decimals, or percents. Now, in order to do that, all we really need to know is what the denominator is. We need to know how many numbers are in the whole list. And of course, we know from this example that there are 25. So if we look at the families that have 0 children, there are 3 of those families out of the 25 families in the whole list. 3 out of 25 of the families have 0 children. So the percentage or the fraction of families that have 0 children is 3 out of 25. And that's usually abbreviated as P, which stands for either probability or proportion. So F, frequency, stands for a whole number. It means how many families there actually were in the survey. Whereas P, a probability or a proportion, tells you what fraction of the families had that quality. Now, so if we just take each one of these numbers and put it over 25, each one of them becomes a fraction. It's very easy to do. I'm not going to bother with reducing them. If we add all those fractions together, we're going to get 25 out of 25, which is just another way of saying 1. Of course, each one of these fractions can be turned into a decimal. If you just pick up your calculator and divide 3 divided by 25, your calculator will tell you that that is 0.12. So each of those fractions could be turned into a decimal. Those decimals would add up to 1. And then, of course, each of those decimals could be turned into a percent if you just shift the decimal point 2 places to the right. So 0.12 is equivalent to 12%. 0.2 is 20%, and 0.04 is equivalent to 4%. If you add all these percentages together, you get 100% of the list. So I'm hoping and assuming that most or all of you are comfortable working with fractions, decimals, and percents. Usually I have a few students who need extra review on that, but not enough to really make it a big part of this class. So if that does apply to you, be assured there's a lot of material online about how to handle fractions, decimals, and percents. And we're not going to do crazy arithmetic with them in this class, just some basic conversions. Okay, so these are, again, whether we write them as a fraction, a decimal, or a percent, these numbers are all going to be less than 1 now, because each one of these categories basically is less than the whole list. And we now call them capital P, which we can think of as either probabilities or proportions. And they're also sometimes called relative frequencies. All of these are equivalent. So in other words, I could, as long as I keep this leftmost column, I could pair it with the second column or the third column or the fourth or fifth column or any combination of them that I wanted to. And all these tables are really equivalent to each other. So that raises an interesting point. Let's say that I gave you a table that started with fractions, decimals, or percents. And then I asked you, how would you turn a column of probabilities into a column of whole number frequencies? So this is a whole new distribution now. let's suppose that we have numbers in a list that are all 5, 10, 15, 20, or 25, occurring with the probabilities or proportions given in this column. So 15% of the numbers in this list are 5s, for example. So the question is, are we able to basically reconstruct the list and figure out like how many 5s were actually in the whole list? 15% of them were 5s, but how many is that? I guess literally we don't really know, because we don't know how big the whole list was, right? We don't know if this means 15% of 38, or 15% of 100, or 15% of 3,249. I don't know. But the astonishing answer is, for purposes of doing math with this distribution, you can actually set n to be whatever you want. It won't affect the math. It won't affect anything about the math except the actual size of the list. So that one number, that the size of the list, is lost forever. But everything else of importance in this list, for example, averages or percentiles or medians, we can find them by just choosing n to be anything we want. Amazing, huh? So I'm going to pick the easiest example, and I'm going to say, let's suppose that this list represents 100 numbers. So if there were 100 numbers in this list, that means that 15% of the list would just be 15 numbers. So I'm just basically copying and pasting all these percents, really, and assuming or pretending that they each represent an actual number of entries in the list. And once I put those numbers there, then you can ask me a lot of different questions about this distribution. Like I said, for example, its mean or its median or its standard deviation, and we don't know what all those things mean yet, but the point is that I can calculate them now. So that's pretty cool. Okay, that's the concept of a relative frequency distribution. Let's discuss cumulative frequency distribution. Here is the distribution, the first two columns of the distribution copied again with whole number frequencies, and we want to ask about the cumulative frequencies. Well, this just means that as we go down the rows, we keep a running total. So if we counted up all the zeros in the list, we would have 3 of them. And then if we also added up all the ones, well, there are 5 ones, so that would make 8 numbers altogether so far, right? We'd have 0, 0, 0, 1, 1, 1, 1, 1. That's 8 numbers so far. And then if we add the 2s, we would have to add 7 of the 2s for a total of 15 values in the list up to that point. And then there are some 3s. There are 6 of them. 21 numbers in the list so far, 24 values up to that point, and 25 values by the time we're done. So you can see that the cumulative frequencies have to grow. You could never have like a 3 here and then 8 here and then like a 5 here. No, a cumulative frequency can't go down because it includes everything below it and then adds more content to it. We can also do that, of course, with probabilities. So this is the probability distribution version of that list, and you might want to take a minute and think about how you would fill in these cumulative probabilities. What number would you put here? We start with the first probability in the list, and then what do? We'd have to add the 35% more, and then keep adding. By the time you're done, you should have 100% of the list accounted for. Again, this topic isn't going to be a big part of the class, but it does come up in the online version of discussion 2. Okay, finally, what is a grouped frequency distribution? This is useful for long lists of numbers, so I've created one on StatCrunch. What I've done over here is I've populated column 1 with 100 random numbers that range from 1 to 100. All right. This is called a discrete uniform list. That's basically how I arrived at this list. But if we turn this into a frequency distribution, Can you kind of visualize why that would be not very helpful? Because probably each of these numbers is only going to be repeated once or twice. So we're just we're almost going to end up just taking this list and ordering it, and then like indicating that each number is repeated probably 0, 1, or 2 times. But it would still be a really long list. It would be very unwieldy. I like how StatCrunch actually like tries to stop us from doing that. If we go to Stat and then click on we click on Data. Oh, now I have to remember how to do. Oh, okay, here we go. Stat Tables Frequency. We're going to work with the discrete uniform 1 list. We want its frequency. And if I click compute here, it gives me a warning. Uh-oh, StatCrunch says, whoa, lots of unique numeric values. Do you want to turn on binning for this procedure? I will in a minute, but I want to show you what it looks like if we don't. So I'm going to click cancel here. So this is a literal frequency distribution of the list. So you can see that it's still super long. And it didn't summarize very much. It basically just kind of repeated the list of numbers itself. It put them in order. Some of them are missing, okay. But then each one of them is repeated like 0, 1, 2, or 3 times. It's not much of a summary. So if we want a shorter, condensed version, we group the numbers. And that basically means that instead of counting individual numbers, we're going to group them into 10s or 20s. And there are some guidelines for doing that. I noticed that StatCrunch does it automatically, but I'll kind of run through them here for you. I need to check my time again. All right, we still got a few minutes. Sometimes I see a timestamp down here, and sometimes I don't. It makes me kind of nervous. All right, so the point that I was making is that when you group your numbers, if you have to do it by hand, you can use some guidelines here. You should choose roughly 5 to 10 classes, as opposed to like 90 in the last example that we saw. You should group them into equal class widths. So for example, by tens, instead of saying 1 through 5, 6 through 18, 19 through 35, or something like that. The first and last classes shouldn't be empty, and you should avoid open-ended classes like 100 or more. So let's see how StatCrunch does it. If we go back here to Stat Tables, Frequency, Discrete Uniform 1, Frequency, Compute, it's going to ask us the same question. And this time, do you want to turn on binning for this procedure? Binning is another name for grouping. Bins, groups, classes are all different words for the same thing. So I'm going to click OK this time. And this is the output that we get now. So what StatCrunch is doing is it's saying, well, there are several numbers in this list that range from 0 to 20. In fact, there are 22 of them. And then there are 16 numbers from 20 to 40, ... And there are 2 numbers from 100 to 120. This probably wasn't the very best choice of bins because the numbers only go up to 100. But it did basically follow all the guidelines that I just set out. So there are 5 to 10 classes. They have equal widths, right? They're counting by 20s. The smallest and largest ones are not empty, and there is no open group like 100 or more. So that is actually satisfactory. Okay, I believe we have killed section 2.1. We did cover all this material. Okay, great. So I'll see you in section 2.2.